So I'll talk about perception and action in the open world, kind of a loaded title. And really what I'll use this as an excuse to do is to talk about some recent work that's been going on in our lab, that some of which will appear at the CVPR. And just to give a little sort of background, so a faculty at CMU, but I also am a director of Autonomous Vehicle Research Center at CMU, and also a principal scientist at Argo AI. So I kind of, in some ways, come at this problem wearing both an academic and industry hat and sort of a bridge thereof. Okay, so clearly, given the nature of the workshop, we don't have to motivate while we're looking at this. And like I said, I'll kind of use this as kind of an opportunity to talk about some recent ways we've been thinking about this problem and sort of highlight recent work that hopefully, if folks want more information about, they can look at in the proceedings. Okay, so how do we sort of set the stage and motivate ourselves for tackling some of these challenges? And I roughly split them into three parts. How do we, process a streaming suite of sensors to understand what's happening in the world? How do we deal with the kind of long tail of all the crazy things that could happen? Then finally, even though let's say all of us come at this from more of a perception or vision perspective, how do we sort of open that up to really think about the full autonomy stack? And I think this dovetails nicely with the previous talk of, so one approach for doing that is really end-to-end reinforcement learning, and I'll try to give another flavor of that here. Okay, so first, let's motivate ourselves. So one of the kind of remarkable properties of working in a space like this is that, of course, it's a safety critical challenge. There's tremendous oversight at the federal level, and so we can kind of do a bit of navel gazing. If we can look at cases of autonomous vehicles of failures, and look at the NTIS, the National Transportation Safety Board report about what failed, and sort of try to understand, okay, given the current ways we're tackling this problem, how do we think, what are the real safety critical challenges? And so here's a case of people may know of a vehicle in autonomous mode that stroke, and unfortunately it was a fatality, killed someone walking a bicycle across the street. And I think there's a lot of lessons that can be learned about how to sort of set up the safety apparatus, which is a difficult thing to do. But from the vision perspective, there's actually a lot of technical discussion of like what were the challenges of understanding the world. And I like this phrase right here. The automatic driving system changed the pedestrian's classification several times, alternating between vehicle, bicycle, and other, because the system never classified the pedestrian as such. And the system's design excluded tracking history for non-persisting objects, those with changed classifications. It was unable to correctly predict the pedestrian's path. So what is here is actually a timeline of T minus seconds up until the collision of the actual classification of essentially the vision system. And so the reason why I sort of highlight this is that I think that, in my view, one of the fundamental challenges here is that it seems very difficult to build stable interpretations of a dynamic world. And one instantiation of that is this notion of, oftentimes, if we look at the output of a vision system or even a prediction system applied to a stream of frames from a video, we might see flickering. So the interpretation of what happens in one frame is different than the other. And usually this is an argument for why we need some kind of temporal processing. And one way we can kind of enforce temporal stability is essentially some kind of low pass filter or smoother that says the world shouldn't change too much. But from another perspective, you could interpret flicker as a good thing, in that it's showing the system self-correcting itself. That it could be that the previous interpretation of the world was incorrect. And because there is a person or a vehicle moving out from behind an occluder in this frame, the world has changed. But then it seems resoundingly difficult to build stable interpretations of this dynamic world. And so what we've been trying to think about is, what are other perspectives that allow us to do this? I think this is one of the reasons why single frame processing is still so popular and kind of frustratingly popular, because it allows you to kind of self-correct. as opposed to building models that integrate over long time spans. So one way to sort of try to build stable interpretations of a dynamic world is to really, I would kind of argue what tends to happen now is that we tend to focus on very accurate, sort of instantaneous measurements of the world. So this is, the output of running a detector on frames from a video sequence. And if you buy the argument that I made before, or that I'm sort of implicitly suggesting, is that, okay, we should just try to build better single frame predictors with high accuracy, because that allows us to accurately understand the world. And we want to do this as fast as possible. So from one perspective, I'm not saying anything new. So in fact, it's readily agreed upon. And if you sort of open up recent papers on various flagship vision tasks like detection or segmentation, they often have graphs like these, where in one axis they'll have accuracy, and the other axis they'll have inference time, how long it takes to process a frame. But what I argue is that this is actually not the whole picture, and that doing well with this kind of graph won't help us solve the problem that we showed in the previous slide. And one way to sort of to try to illustrate this is the kind of visualizations that we tend to show on the left-hand side. But if you actually go sit in a car and look at the live stream of sensor data and interpretation that's happening, what you see is something very different. And what you see is something that looks a little bit like the right-hand side. And for the longest time, this confused me. Of like, is this just a visualization bug? Are we not sort of showing the right frame with the right output? But I argue that the right-hand side is not a visualization bug. And that it reflects this undeniable fact of what I would call sort of embodied perception, and that by the time an algorithm finishes processing a sensor measurement, the world has changed. And that is what's causing this misalignment. Now, you can artificially make the right-hand side look better by showing a historical image of the world as it was when the algorithm started processing that frame. But that's not really real-time embodied recognition. The right-hand side is we have to act in the world that's instantaneously in front of us. The argument that we want to sort of motivate here is that there's actually, I think, kind of a subtle, perhaps confusion or a subtle question about what does it even mean to be real time? And so there's various benchmarks that have been defined, oftentimes in the tracking community, and then also in recent AV benchmarks that I think we'll talk about in this workshop as well, where one definition of real time could be you must finish processing before you get the next sensor measurement. And I would call this like a fast detector. But then what I argue is that at some level, it seems like this can't be the right, at least theoretical way of thinking about this, because this is tying the definition of real time to your frame rate. But the frame rate is not a constraint. It's a design choice, just like we choose the hardware and we choose the camera sensors and we ultimately choose the acquisition rates. And furthermore, different sensors have very different frame rates. LiDAR famously typically works at 10 hertz. And so, if we have a person or a child that appears behind an occluder in between two sensor measurements, I don't think it's appropriate to say that, oh, we're not responsible for perceiving or acting in response to this person that appeared behind an occluder until the next clock cycle. Like ultimately, we have to sense and act in a continuous world. And so there's this, we're sort of building on a body of work that we presented at ECCV 2020 called Towards Streaming Perception, where we advocate for a different perspective on how to think about this. And that is, we require an algorithm to report the state of the world at all time instants, even if it's not done processing the previous frame. And what that means is you can choose to run a more accurate detector that's slower, let's say, but when the detector is running, it can't be, it doesn't have access to, or rather the right way of saying it is that when the detector is running, it still is responsible for outputting the state of the world at all time instants, because essentially that's the way in which we have to act. And if you think about how to actually define this as a benchmark, it's actually rather simple. So we're showing you on the left-hand side, the real-time prediction of just running a detector on a live stream of data. On the right-hand side, we're showing you, let's say, a visual of ground truth. So offline, we can label every single frame on that data with what the state of the world is. And now we can literally measure the accuracy of this prediction. We can benchmark it against the ground truth, given on the right-hand side. And so what this allows us to do is essentially turn any kind of single frame metric into a streaming metric. And this is very much related to work on real-time or anytime algorithms. But historically, that body of work suggests that oftentimes that views compute through a contract lens that says your algorithm must finish by the next frame. And so even if it's not done, it has to output a partial answer about the world. And in our view, what we're saying is the algorithm can decide when it finishes. But if it chooses to take longer to process a frame, well, then it has to spit out some intermediate answer about what the world is doing. So essentially, I'll just sort of give you like a preview of results. So the left-hand side is if you just run a detector that's, let's say, been optimized either for speed or for accuracy, it ends up being not great in terms of this real-time metric. But then if you actually optimize for this streaming accuracy, you end up sort of trading off between not running a detector that's so fast that it compromises accuracy and not running a detector that's so slow that it ends up lagging behind the world. So if you define this as just a criteria, it turns out you can optimize for this. So instead of having essentially a cross entropy loss that's minimized, you can minimize a streaming cross entropy loss. And when you do that, a number of surprising behaviors emerge from systems optimized in this way. I'll mention that this award, this paper won the Best Paper Honorable Mention Award in ECCV, the same one that NERF won, but NERF has clearly had a lot of fanfare. But what we've done is we've actually held, Martin, the student behind this, has put together a benchmark competition that I'll talk about in the next few slides. And so we're hoping folks kind of gravitate onto this view of real-time processing, which we think is sort of a fundamental property of, I think, any embodied perception system, including self-driving vehicles. So ultimately, there's this, so what are some of the interesting behaviors that emerge if you take this perspective? So these plots that we see in commonplace that trade off accuracy versus latency, it turns out that, you could imagine, optimizing one side of this where you build very fast detectors that operate within the frame rate. And you could imagine optimizing the other side of this where you build very accurate detectors, but end up being really slow. You have to skip a lot of frames. At this, if they take 200 milliseconds, you'll have to skip on the order of 6 or 7 frames. And it turns out neither of these end extremes actually optimize the streaming accuracy. It turns out something in the middle does. So there's actually a sweet spot that trades off sort of accuracy versus the reactiveness of the system. And if you think about this a bit more, the sort of simplest thing you can do if you're still trying to, if you've analyzed the state of the world the last time that you saw a frame, but you're still responsible for reporting the state of the world while you're processing this next one, the simplest thing you can do is say, all right, I'm just assuming the last time I opened my eyes, this is where I saw the objects, this is where I saw the semantic labels. I'm going to assume that holds still. But you can imagine that that's almost like a zeroth order model. And what is arguably much more effective is a first order model that says, well, if I've seen things move a certain way, I'm going to assume that all things being equal, that the world is ballistic, that it continues to change the way that it has been changing. So what that suggests is if you really want to optimize this sort of streaming real-time accuracy, tracking and forecasting, meaning you sort of estimate how things are changing and you propagate those estimates forward in time while you're busy processing the next frame, they emerge as things that that optimize this streaming AP, which is kind of neat because ultimately this is just a single frame metric. But it turns out that tracking and forecasting helps you achieve this better accuracy in the single frame metric. But in order to do this, you have to have extremely lightweight tracking and forecasting solutions. And one of the things that we saw is that when we try to evaluate, current trackers and current forecasters, they become incredibly, it ends up, if they take a lot of compute, they slow you down and they make the system lag even more. So it's sort of this way of sort of formalizing it forces you to be honest. And there's some other sort of surprising results that emerge from this perspective. And one thing that was kind of shocking to me was that you could imagine that current systems, they oftentimes in sort of in sort of a robotic environment, you operate in sort of an asynchronous fashion. So if you're busy processing the frame and then you finish processing your last frame, then you go and you grab the next frame that's available on some buffer and you start processing that. And what we find is that actually might not be the optimal thing to do if you define this metric and really optimize it. And that sometimes it's better to wait and sit idle and wait for a new frame to arrive, as given by this orange region here. Wait for a new frame to arrive rather than start processing an existing frame that will soon become stale. So this has again, to me, kind of a very surprising result that if you really want to maximize responsiveness and reactiveness, sometimes the best thing you can do is actually to sit idle and wait for a fresh sensor measurement to arrive rather than just kind of grab one that exists right now. And so what this really suggests is that to really optimize this sort of streaming metric, you need to asynchronously schedule when you decide to compute. So what ends up happening is that there's a lot of kind of behaviors that emerge by sort of formalizing this metric in this online fashion, and then actually optimizing architectures for this. And then finally, even though I motivated this very much from the AV perspective, another sort of personal motivation of mine is that I think this is very much true of human vision and biological vision. So it's very well known that human reaction time is roughly around 200 milliseconds. So the time it takes from when you perceive something on the retina to when you can sort of manipulate your hands through sort of neurological commands is 200 milliseconds. And so what that means is that if athletes are performing highly skilled maneuvers, such as hitting a fastball that's moving 100 miles per hour, what that means is when they are actually moving or controlling their hands and bodies, they're actually using a stale measurement from their eye. Essentially, if I'm trying to hit a ball that's moving 100 miles an hour, the image that I have of the ball is actually 30 meters offset from where the bar will be when I'm able to move my hands to strike it with a bat. And so what that suggests is that humans must fundamentally be making use of tracking and asynchronous forecasting. And there's lots of evidence that suggests this is the case as well. So I kind of mentioned that we think this is a pretty kind of, or we hope that this is an interesting way of evaluating algorithms in a latency-aware fashion, and it kind of allows for sort of creative architectures to kind of bubble up. We actually held a streaming benchmark that Martin and collaborators will talk about later on today, where instead of optimizing average precision, you optimize streaming average precision. And there's a lot of sort of frameworks that have been built up for how do you, one of the annoying things about, so in full disclosure, one of the annoying things about this perspective is that now when we talk about the accuracy, the average precision of an algorithm, it depends on the hardware that you use. Because if you have access to more GPUs or better GPUs, the algorithm won't lag as much, and so it will have better accuracy. And so from one perspective, you think this is really frustrating because now it complicates our discussion and evaluation of accuracy. But from another perspective, I would argue that that's fundamental to embodied perception. When you go run things on a car, it does matter, the hardware that you use. And essentially embodied perception means that the body depends, the way in which we sort of measure accuracy and develop algorithms should be intimately tied to the bodies that we use. So this is both a blessing and a curse. And historically in vision, we haven't really embraced this kind of evaluation. But I think this is sort of needed to, as we move toward, implementing real systems in creating safety critical settings. So I hope folks would consider sort of joining in on this, because I think it does offer some interesting perspectives. And one of the things that we found, for example, is that attentional processing, not in the sort of transformer notion of attention, but this is more in the human vision notion of attention, that we should spend more effort on certain pixels in the image where we think interesting things are happening and less effort on others. It turns out that attentional processing also emerges as a very effective strategy for optimizing streaming accuracy. And again, this is sort of, to me, very comforting in that it seems like that's in some ways a fundamental part of human biological perception. We attend and we saccade, we focus on certain things. And that kind of adaptive processing is not as common in practical AV systems. Okay. Riffing off of this notion of sort of tracking and forecasting emerge as sort of first-class citizens, even if you care about single frame accuracy. We also have some pretty extensive efforts of creating a large-scale tracking challenge that really looks at diverse data, and even not just AV data, but sort of as much kinds of video content as we could. And so I've urged folks to look at this as well. And the hope is to sort of create kind of a large-scale test bed for the unique perspective that we're trying to sort of focus on. This is that focus on the fact that rather than sort of work with or fix small-scale ontologies, if we really believe in perceiving things in the open world and urban corridors, we need to be able to detect and track and react to almost anything. So really, essentially, this is a large vocabulary tracking setup, which we find is relatively rare. Usually, we tend to focus on, just cars or people, but in reality, we have to handle everything. Okay, I'll just quickly sort of finish with a couple more sort of thoughts. Sort of riffing off of this last comment I made as well about knowing that some object is present is super crucial. I feel like this is maybe another big lesson I've learned from my time in the AV industry, which is I feel like a lot of vision is really focused on sort of semantic classification. We work with ontologies and lists of labels. And the example I like to give is pretend like a trash can rolled over in the street and debris and clutter rolled out of it. It somehow doesn't make sense that we have pre-built detectors and semantic labels for each of these things. And it feels like instead it's much more important to note that there's some object here that exists and that is moving. One thing that we've been focusing on a lot is the role of motion in trying to build generic open world systems. And so I'll sort of make perhaps a controversial claim or perhaps not. When I show the examples in this previous frame of just weird debris that's lying on the road, and how do we build models that can react to any sources of such debris, I think it's very natural to think about geometry and shape. So this is where if we can understand that there's some 3D obstacle, that we can avoid it. And so this is why 3D sensors are so ubiquitous. Clearly sensors have an incredibly huge role to play here. And something that we've been exploring as well is, well, how far can you get with a camera? And so there's been an enormous amount of work in the field on how to build systems for inferring 3D shape and structure from images. And the perspective that we've been trying to advocate is, let's not do it just from a single image, but from multiple frames. And in some ways, that's a very old perspective. This is what Structure for Motion, or SLAM, does. But historically, those methods have really been tuned for rigid scenes. And I go back to the motivating scenario of, I think the crucial question here is, how do you build, I guess, 3D models of a world that's dynamic and changing? And so we've been focusing a lot on sort of extracting motion as a first-class primitive. So there's been some work on estimating. Here's kind of an interesting phenomenon that's always intrigued me. The fact that low-level primates and insects and rodents can navigate quite well, like a fly. But then it doesn't seem like they would do that by semantically recognizing things that are happening. And in fact, there's lots of sort of evidence to suggest that motion plays a huge role in lower level organisms for navigation. So one thing we've been looking at is, motion is clearly a very historic task that's been examined at length in the vision community. So optical flows, the classic problem of estimating how pixels move in the U and V direction. one thing that we've been looking at as well is there's an extension of optical flow, which surprisingly in the computer vision community hasn't really been examined that much, which is called optical expansion, which is not only you can track a pixel as it moves left or right, you can track a pixel as if it gets bigger or smaller. And the reason why that is so useful is that reveals something about the change in the depth of that pixel. As things get closer, they get bigger. And so, in fact, what I'm visualizing on the bottom image here, although it looks kind of like a depth map, what it's actually visualizing is the rate of expansion of every pixel. And so, this is optical expansion. It's fairly readily extracted from image pairs, and what this gives you is actually you can do some sort of back of the envelope calculations from your intro vision class. And what this really tells you is time to contact for every pixel, because things that are getting bigger, you're more likely to hit. And so what's interesting is that I think time to contact is something that we haven't been looking at a lot in the vision community, but it's related to, but it's different than these other flagship low-level tasks like depth estimation or motion estimation. The canonical example I would give is that, if you're moving slow toward a close-by wall, or if you're moving fast toward a far-away wall, it could be that both of these things have the same time to contact, but they both have different depths, they both have different motions. But what's interesting is that the way in which you interact with them, the time to contact value is the same. And that's actually in some ways a more robust quantity to extract than either of the other two. So we've done some work on sort of trying to advocate this as perhaps another flagship low-level or maybe even mid-level vision task. I want to point out that this is not our work, but a nice piece of work also looks at time to contact, and this was one of the best paper finalists this year in the CVPR. So it's the derivation is sort of, there's math behind it, but the intuition hopefully is natural, that if things are moving closer to you, they get bigger, and so you can measure that. And in fact, we've been building off of this work to build systems that can detect and segment and track any kinds of objects, but essentially using motion as the cue as opposed to appearance. And one of the things that we sort of encountered along the way, this is surprising to me, was that if you have two frames with like what kinds of moving objects can you detect and segment? So here's a very common case. You're driving down the street and there's another car moving in the opposite direction. And so we asked this interesting question, can you segment out this car? Can you identify that this is all the pixels on the car are moving in a different way than all the pixels on the rigid background? And it turns out that you can't. The way I should say that is that there is a 3D interpretation of those two frames that is consistent with a purely rigid world. And that 3D interpretation pretends that car is floating above the ground. So it turns out that you can't strictly just from image measurements figure out if that is a stationary object or a moving one. But of course, the reason why we are able to resolve that is that we have geometric priors. We don't believe cars are floating above the road. And it turns out you need to sort of insert those in to resolve these ambiguities. So we have almost a sort of a theoretical work that looks at when can you segment out objects from a moving flow field and actually build these observations into a network. That essentially is an object detector that based purely on motion. And so it's essentially a rigid object detector. And you can kind of see the behavior of this thing here. Not only does it detect rigid objects that are moving, but it also estimates sort of overall camera motion. And the goal is that this kind of thing can help you identify objects without needing to name it. Apologies here, the reference shouldn't be archived. It's a CVPR paper. The other thing that this points out that the earlier speaker mentioned is that this points out the subtlety in identifying moving versus stationary things, which turns out to be an incredibly important and surprisingly difficult task. As a car is parked and slowly starting to move, the way that you should interface or react to it is very different. So estimating very small motions is incredibly important. And so I think that sort of building better flow and motion estimation modules I think will be an important part of the final answer. And it can now allow you to, now we can sort of do things of, detect and track people on e-scooters, even if we've never seen that before. We don't have to have a training data set where we have these kinds of special mobile pedestrians, just by virtue of how we've designed this thing. And one more cool thing that we've done with this, I'll sort of, the shameless advertisement, I'll maybe stop here, is that we've used these motion estimates to build models for essentially inverse graphics processing of video sequences. So what I'm showing here are essentially it's 3D models that have been fit to video sequences, just using essentially, very classic, almost analysis by synthesis or inverse graphics rendering engines. And the trick to getting all of this to work was essentially using flow as an input to all of these systems. So the reason why I'm sort of super intrigued by this is that, at least historically, when we've seen videos like this, in my experience, to get this level of accuracy, fidelity of a person with clothing, you either need lots of cameras in some capture studio, or you need very strong prior models. You've built up scans of people, and you expect the person that you see here to look somehow like the database of scans that you've built up. Here, nothing like that was used. It literally is starting from a generic sphere interpretation of the object that's in the scene, and it just keeps deforming this to an inverse graphics rendering engine to match the data in the scene. So this thing can now essentially detect and track camels, even though it's never seen one before, just by virtue of essentially matching to the flow data that we see in the image. So I think this is also...
Hey, Deva?
Yes.
Your time is actually up, and our time is quite tight.
Got it.
Is there something you really wanted to kind of highlight?
I'll just end here. So sort of like the 30-second view summary was that, so in terms of temporal streaming processing, we think there's other ways of looking at the problem that really embraces this notion of like online real-time analysis, which I think is fundamental to embodied perception and self-driving in particular. And then in terms of the building systems that can really understand what's happening without requiring massive amounts of training data, open world systems that make use of motion and shape as first-class primitives. So I'll end there. Thank you.